Hi all, I realize it's been quite a while since I made a video on the H8 project's progress. As you might remember from the last video, I got the H9 terminal repaired and running, which leaves only the H17 dual disk drive to get going to have a complete H8 system. And if you haven't watched the previous parts of this series, you'll want to watch them first. I'll include links in the description, or you can click the link above. So that's what I'll be sharing in this video, and the best place to start is to take a quick look at the H17's condition. This H17 unit is pretty dirty, but otherwise not in too bad of shape. It's obviously been stored in a dusty location like a garage or a storage unit, but it is complete with its cables and its controller card. The card looks okay at first glance, and all the components and chips are present on the PCB, so that's good. There's the usual black tarnish on many of the IC pins, but that easily cleans up, and it usually doesn't present a huge problem anyway. Just as a preparatory step, I pulled all the ICs out, and I used some deoxit on the IC sockets and then reinserted all the chips. I also did a quick measurement on the power regulation circuitry, paying close attention to the tantalum capacitors that can fail shorted. And I've had issues with those on other parts of the H8 project. Thankfully, the caps on this board were all rated at 35 volts. Where I've had problems with other componentry is when they use the small 25 volt rated little blue tantalum capacitors. With everything seeming okay on the controller board, I went ahead and installed it into the H8. Once installed, I performed the two tests listed in the H17 manual. Both of these are memory tests, and these are stored as routines on the controller card's ROM. So the first test goes through the computer's memory, and then the second test tests the memory on the disk controller card itself. Both these tests were pretty lengthy to perform, so in the video I've sped things up a little bit so that you don't have to sit through the entire memory test. Well, after several minutes have gone by, both of the tests passed the first time. Unfortunately, though, in subsequent tests I did not perform consistently, so sometimes it passed, sometimes they didn't. And then after removing the controller card for a little bit closer inspection and reinserting it, the test started failing consistently. So the problem ended up being a mechanical problem at the card edge connector. I did a little continuity testing just to kind of verify the problem, and a quick visual inspection showed that there was damage and corrosion to the top connector on the controller card. But mysteriously, somehow the bottom one looked absolutely perfect. So it was on to removing the bad connector and installing a replacement, and I've got to give a special thanks to Glenn from the Society of 8-Bit Heath Computerist Google group, who provided me with a few replacements so that I could replace this one and any other ones that I might find that were bad. So once the connector was replaced, the card then consistently passed all of the memory tests. With the controller card out of the way for now, it was time to give the drive chassis some attention. I usually start with a little photo documentation before I start tearing things apart, so I know how to put them hopefully back together again. And I can also get a chance to see what the starting condition was of the components that I'm working on. Well, here's where things start to get a little ugly. I noticed the cover over the AC input area was loose. I moved it out of the way, and I found an alligator clip lead attached across the fuse holder. This is never a good sign. I spent some time to pull out the broken fuse holder and replace it, but I'm pretty sure that some damage may have already been done from it being jumpered with the alligator clip lead. My guess is the fuse holder was broken from frequent fuse changes during high current draws somewhere else in the H17 unit, and once the clip lead was installed, who knows what happened. After dealing with the fuse holder, I pulled out the main power PCB for a closer inspection and noticed that one of the large electrolytic capacitors was discolored and possibly leaking. I also discovered a tantalum capacitor that was shorted, so I replaced that, and one other with a new 35 volt cap where the originals were only 25 volt tantalums, the little blue ones that I really hate and seem to almost always be a problem when I encounter them. Another small electrolytic was also very drastically out of range, so I replaced it. Once all of the bad bits were replaced, I reassembled the power supply section and powered it up, and all the voltages measured out perfectly. Now it's time to take a look at the two Wanko 82 floppy disk drives. I started by removing them from the H17 chassis and doing a quick visual inspection. The drives are fairly clean overall, but it was clear that the old bearing lubricants had dried up a long time ago, and that's something that I would have to spend some time to address. Next, I removed the PCB from the first drive so I could get a little closer look at what was underneath, and things appeared to be in pretty good condition, with no signs of physical damage or corrosion or previous work. I took a moment here to measure both the 12 volt and 5 volt rails to check for shorts, and I discovered that the 12 volt rail was shorted to ground. The culprit in this place was another tantalum capacitor. This time it was one of the black bullet tantalum capacitors on the board, so a little different than the little bead type capacitors that we've seen elsewhere. And this short was most likely the source of the problem with the previous owner, and maybe what led to all the frequent fuse changes that may have damaged the fuse holder and caused the subsequent power supply damage. I spent a few minutes to look at the mechanical side of the drive and kind of identify the location of the bearings and lubrication points that I would need to address. Now at this point I started to disassemble the drive, and I noticed again as I tore down the drive how clean it was, and it's free of excessive dirt and corrosion. So actually that's a pretty big relief. The electronics we can fix, but mechanical problems with the drive might be a little bit more difficult, especially if it required any kind of parts replacement. One thing that I did notice was that the top spindle took a lot of force to turn. So here I removed the main drive pulley, I inspected the belt, which was in good condition, and after removing the bottom spindle, I spent some time fighting with the C-clips that hold the two spindle bearings in place. Both these bearings were almost completely frozen from the old grease inside the bearing. I gave all the bearings that I'd removed up to this point an overnight bath in some silicone-based 3-in-1 oil. I now turned my attention to the upper spindle assembly and took to totally disassembling that and pulling the bearings. One of the things I found here was that one bearing was so stuck that I actually had to do a WD-40 soak before I relubricated it with the silicone-based 3-in-1 oil. I usually don't like to use WD-40 on these types of things, but it was just really stuck. So after letting things soak overnight, the next day it was time to wipe off the bearings and check out the results. All of the bearings now spun free, so it was time to reassemble the drive. The reassembly seemed pretty straightforward, but this is where I made a big mistake that would come back to haunt me, and I'll share a little bit more about that later. With the first drive reassembly complete, I gave the main H17 chassis a quick cleanup, and then reinstalled the completed drive that would become SY0 or SYS0 drive. Next, I wanted to run a speed check on the drive. The H17 operation manual has a short program listing towards the middle to do this, so I entered it into the H8 and then recorded the speed test program to cassette so that I could reuse it without having to completely re-enter the program again. I should mention at this point that I had repeated the cleanup and lubrication procedure on the second Wanko 82 drive that I would be using for SYS1. When running the speed test on the first drive, I got almost perfect results. Ideally, the reading should be very close to 177, and the drive showed a steady 176. On the second drive, I got a reading of 172, and for me this was close enough to ideal as to not mess with the speed adjustment on the drive. Everything seemed good, but here's where the train left the track. Unfortunately, I didn't take any video of what occurred, but there really wasn't much to see. The drives would not pass the basic tests in the H17 manual, specifically the final step on page 6. The test returned an error code of 037306 to the H8 display panel, even after repeatedly following instructions for verifying both the speed test and the write gate test. At this point, I decided to use my email a friend lifeline to see if another set of eyes would catch what I was missing. So I emailed Glenn from the Society of 8-Bit Heathkit Computerist Google group, and he generously offered to look at the drive. He quickly found the problem. I made a mistake when I reassembled the drive by trapping the pressure arm underneath the baling frame. This also caused the small felt pad on the pressure arm to become dislodged. After Glenn corrected the assembly error that I'd made, the drive performed absolutely flawlessly. And wouldn't you know it, I made the same mistake on the second drive, which I quickly addressed. With both Wanko drives home and mounted into the H17 chassis, it was time to test things out. It's at this point that I rather nervously decided to insert my only copy of HDOS 2.0 into the drive. And this is on a rare 5¼ inch 10 hard sector disk, and I've been having a terrible time finding any of these, and I had some generously given to me, but I'm still looking at a good way to make those out of just kind of standard disks. I know there's a lot of projects out there for coming up with custom hole punches and such, but I don't have access to any of those. So putting this one and only disk that I had into the drive, yeah, I was a little nervous about that. But I put it in, I turned on the H8, and I hit the go button. So my particular H8 has the PAM-Go ROM, so all I really had to do at this point was to just insert the disk and then hit the go button. Much to my elation, the system did jump to the action prompt, and after hitting the return key, I found myself booting into HDOS. When I got down to set the date, I decided it was appropriate to leave the date set to March of 1978. I'll have to find out if HDOS was Y2K compliant later, although I don't think it was, as I seem to remember I saw some information about a Y2K patch for HDOS, so I'll have to look more into that. Well, now that I have a working disk drive, one of the things I want to do is to run the H17 program that comes on the HDOS 2.0 disk and give the drives a thorough shakedown. Now, in the tests that are coming up, I'm going to let some things run real time, and I'm going to speed other things up or even jump forward significantly in time, because some of these tests range all the way up to over 40 minutes long, and that doesn't make for very interesting viewing. The H17 test program has quite a menu of different tests that we can run on the drive. One of the first tests that I'll be running is to check the drive's rotational speed. Now, we've already done this once using just the short front panel entered program that I displayed earlier, and according to that program, the rotational speed was just about right on. So, using a blank initialized disk, this program will do pretty much a similar thing, and what we want to see is a 1.0. That would indicate that our drive speed is just spot on, and that's pretty much what we see here. So just as we discovered before, the drive's rotational speed looks great. The next test determines the step time for the particular drive. Heathkit, on its disclaimer that you actually see scrolling up on the screen here, specify that their step time that they're looking for is 30 milliseconds or better. And different drive manufacturers could have different specifications here, but a worst case scenario is 30 milliseconds. Now this is a pretty lengthy test. It takes a long time to run, so I've sped it up significantly. So we're looking at a 20 times run here. But what it will do is it will go through a series of specific tests starting at 36 milliseconds, and it will keep speeding up the time until it finds a point that the drive fails, the seek test. In this case, the drive continues to pass all of its tests until it hits 8 milliseconds. So 8 milliseconds is significantly faster than the 30 millisecond minimum that they specify. The next test is actually designed to test the physical media in the drive or the diskette and make sure that it is error-free. And as you can see from the 0 bad sectors located message, this is a good diskette. This final test is a general drive checkout, and this test will run 3 sequential times, and it's kind of more of a stress test to put the drive through its paces. So going through these 3 passes, if there are any issues that come up, they're likely to be caught here. Now this is a very lengthy test, so I have jumped pretty much straight to the end, and as you can see, we've passed all 3 times. So this drive is functioning well and is in great shape. It's time now to exit the H17 test program and boot back into HDOS. And one of the things that I want to do next is to create a backup copy of my system disk, because right now I just have the single copy of the HDOS 2.0 disk, and I'm going to go through the process of initializing a new disk and then creating another system disk. Now I have also done the test that we just covered previously on the second drive too, and it performed equally well. So what we're going to do as we make this system disk is I am going to utilize our second disk, SY1 or System 1, and that's the one that we'll be copying our system disk to. So first thing I need to do is actually type INIT correctly. One of the things that I'm looking forward to is getting a different terminal for this. Actually, the H9 has been great for kind of showing off that original terminal, but I would sure love to have an H19, get lowercase and proper backspace and some of those things. So then I could maybe do a little better with my typing. Also, the keys are really sticky on this H9 keyboard. They tend to bind a lot. Alright, so we're going back through the initialization process again, and we're going to format a new disk or another blank disk in the System 1 drive. And this is actually the same disk we used for the testing, so you can see that it has the label there where it says this disk was erased by test. So we're going to make this a volume 1, and we're going to label this system volume, and the same as our original HDOS disk. Okay, there we are, and our formatting's complete, and I'll just hit return where it says bad sector, because it's asking for bad sectors, and we know from testing this media that there are no bad sectors on the disk. And now we're basically just going to back out of the initialization routine and boot back into HDOS again. Now the next thing we can do is we can use the SYSGEN command, and if we use the SYSGEN command with wildcards, the ***, what that'll do is it will turn that disk in the second drive into a system disk and copy all of the files off of the original disk over to it. So then we'll have a complete backup of that original HDOS disk. And there we go. We have all 20 files copied, the system files, and plus some of the utilities that were on that disk. And the last thing we need to do is to go ahead and swap the disks and put that new system disk over into SYS0 and reboot and check that our disk is working correctly. And as expected, everything is working fine. So now I have a backup of that HDOS disk, and that leaves me feeling a little bit better. One of the things I was a little paranoid about was destroying that first disk in some manner before I had a backup when I was going through this process of, fixing the drives and such. So I'm very glad to have this. With that, I think we're at a point where I can say that we have a fully functioning H8 system with the main system, the H17 disk drive unit, and the H9 terminal. So it's been a long road to get here, and I'm very happy to finally be finished with this project. Now there's really only one thing left that I can think to do, and that is to take the missing H17 floppy drive sticker and put on the badge here, and this is something that I had to make up as the original one was missing. If you've stuck with me clear to the end on this video and on this project, thank you a lot for watching, and this is not the last we're going to see of this particular H8 system, but I do have some other projects in the works that you might see first, again, before you see this. Some of them are other Heathkit projects. So thanks again for watching, and we'll see you again in the next video.